Suppose we have an inverted infinite right circular cone with its vertex sitting at the origin of the rectangular coordinate system. Let's say we pick a point on the conic surface and originate a ray from the origin to pass through the point of your choosing. It's pretty intuitive that the ray lies on the conic surface. If you also put a plane tangent to the surface at that point, it's not hard to imagine that the ray also lies on the tangent plane because the tangent plane intersects with the conic surface at that ray. How do we show these two facts mathematically? Let's get to it. Here is our plan of attack. We will first get the equations of the tangent plane and the ray, and then use them to show the two intuitive facts. So step 1, let's find the equation for the tangent plane to the conic surface. Here is the equation of the conic surface in the rectangular coordinate system. X and y could be any real number. Let's call the conic surface S. Now suppose P0 is a point on the surface S with coordinates x0, y0, and z0. To be a point on S, the coordinates must satisfy the equation of S. So we have z0 equals the square root of x0 square plus y0 square. Here is the general equation of the tangent plane to the graph of a function of x and y at the point P0. Let's call the tangent plane pi. As you can see, other than z0, we'll need the two first partials of z evaluated at P0. To compute the partials, we need to apply chain rule because z is a composite function. The outer function is u to the power of 1/2, single variable. The inner function is x squared plus y squared, so multivariable. Applying chain rule, we get this. Derivative of u to the power of 1/2 is 1/2 times u to the power of -1/2. Taking partial of the inner function, we get 2x. Plugging the inner function into the first part, we get this. Altogether, we have x over the square root of x squared plus y squared. Notice that the denominator is just z, so partial z partial x is simply x over z. Now let's get the other first partial. We're going to use a trick here. Because of the symmetry of z in x and y, we swap x and y in partial z partial x to get this. Now evaluate the two partials at P0. We have all three pieces needed to get the equation of the tangent plane. This is where we left off before computing the partials. Plugging in the partials, we immediately have the equation of the tangent plane pi. Let's label this equation using the pound sign. Now, let's move on to step 2 to get the equation of the ray, which is just a special kind of line. For the sake of convenience, let's call that ray L. We will begin with the vector equation of a line. So let's write down the position vector of the tangency point P0. Call it vector R0. The position vector of any point on the ray is simply some scalar multiple of the vector R0, which gives the direction of the ray. However, as we are interested in a ray instead of a line, the scalar multiple t couldn't be just any real number. It must be a non-negative one, so that you always stay above the xy plane as you move away from the origin along the ray. Expand the vectors in column form so that we can get the equivalent parametric equations of the ray. Let's label this equation using asterisk. Now, we have the basic materials to construct the proofs. First of all is the ray L on the surface S. If that's the case, the coordinates of any point on the ray must satisfy the equation of the conic surface S. It would be equally good enough to show that the coordinates satisfy z squared equals x squared plus y squared. That would be easier to work with. Now, let's start with the right-hand side of the equivalent equation of the conic surface, x squared plus y squared. Plugging in the x and y coordinates of an arbitrary point on the ray L, we would like to see if we could turn this resulting expression to the left-hand side of the equivalent conic surface equation, which is z squared. Factor out t squared. What follows can be replaced with z0 because P0 is a point on the conic surface. So far, it becomes t squared times z0 squared. Rewrite it as the square of t times z0. According to the parametric equations of the ray L, the z-coordinate of the arbitrary point on the ray is exactly t times z0. So we have z squared. Perfect. We've just showed that any arbitrary point on the ray L satisfies the equation of the conic surface S. That means the ray L is on the conic surface S. Alright, next we want to see if the ray L is also on the tangent plane pi. If that's true, the coordinates of any point on the ray must satisfy the equation of the tangent plane. As a reminder, here is the equation of the tangent plane pi. Like the previous proof, we start with the right-hand side of the tangent plane equation and plug in the x and y coordinates of an arbitrary point on the ray to see if we can get back the left-hand side of the tangent plane equation, which is z. Factor out t. The guy that comes after t over z0 can be replaced with z0 squared. Again, this is because P0 is a point on the conic surface S. After simplification, we have t times z0, which is just the z-coordinate of the arbitrary point we begin with. That means we have just showed that the ray L is also on the tangent plane pi. Alright, mission accomplished. I hope you enjoy this video, and I'll see you in the next one.